Okay, thank you. So I'd like to start off with thanking the SLC and the LLC for organizing a wonderful workshop this week, especially for someone who comes from outside the microlensing community. It's been very informative and I've learned a lot this week. So I will be talking about asteroseismology, which, similar to microlensing, is a fairly young field and has undergone quite a lot of change, exciting change over the last few years. And in particular, we'll talk about why the asteroseismology community should be excited or is excited about the WFIRST microlensing survey and what we can do with the data that will result from that. So we'll start off with a bit of a crash course into asteroseismology, assuming that not many of you, and most of you have heard about it before. So this will be fairly quick, fairly pedagogical, high-level overview of what asteroseismology actually is. Now, the first thing you might ask yourself is whether we're actually misspelling the name of our own field. Why is it called asteroseismology and not astroseismology? I can assure you it's not misspelled. In fact, there's actually a paper that explains exactly why it is called astroseismology. I won't go into the details. It was written by Douglas Goff, who's one of the founders of the field, helioseismology as well. If you want to know more about it, you can ask me afterwards. But we are not misspelling. It's actually asteroseismology. Okay, so asteroseismology is the study of pulsating or oscillating stars. And any oscillation mode that we observe in a star, we need to characterize using a few numbers, so a few characteristics. The first of which is fairly easy. It's basically the radial order, which is the number of node lines from the surface of the star. So if here's the surface, and this is the center, and this is the displacement of a wave inside of the star, then the number of zero crossings or node lines, similar to, you basically hold a string and you make a wave. The number of zero crossings, that's the radial order n. So the number of node lines from the surface to the center. Now, stars are, of course, not one-dimensional, but we have spheres, so that means we can also have modes that have node lines on the surface of the star. So if you imagine you take a cross-section through the star, you cut the star open, and you follow an oscillation mode from the surface inwards into the interior, if that mode goes all the way to the center of the star, what will happen is that the star basically pulsates in a radial mode. So it will spherically symmetrically expand and contract. So this mode will have no node lines on the surface. So it's an L equals 0 mode, because L is the spherical degree. L denotes the total number of node lines on the surface. So this will be an L equals 0 mode or a radial mode. On the other hand, you can have a mode that starts off at the surface of the star, but then gets deflected at some depth because of the density gradient and the orientation of the wave. So it bounces back to the surface, bounces back again. So it will form node lines on the surface of the star. In this particular case, this will be an L equals 2 mode. So that means we have 2 node lines that are on the surface of the star. This would be a quadrupole mode. L equals 1 would be a dipole mode, and so on and so forth. So the spherical degree, total number of surface node lines. Now, if you summarize this all, you can describe the oscillation mode in a star using spherical harmonics. So again, L is the total number, is the spherical degree, the total number of node lines on the surface. M is the azimuth for order, which is a subset of L. It's basically the number of surface node lines that go through the rotation axis of the star. So we have N, L, and M, radial order, spherical degree, and azimuth order, which describe an oscillation mode in a star. So here's an animation, a highly exaggerated animation of what a star actually does. Of course, no real star actually pulsates in these large amplitudes. But just for illustration purposes, this is an L equals 2 mode. The red arrows here point to the node line. So there's one node line here and one here. And it pulsates with an L equals 2 modes. None of these go through the rotation axis, and hence it's an M equals 0. So since this is a workshop and a lecture, I thought I'd put in a quiz as well. So we've just discussed the spherical degrees. So here is an example of a model oscillation mode. So let's do a show of hands. Who believes that this is an L equals 0 mode? L equals 1. L equals 2. All right. How about the M? Who believes it's an M equals 0? M equals 1. Yeah, a few show of hands. Yes, so it's an L equals 1 mode. So this is a dipole mode because we have one node line, and the node line goes through the rotation axis, which I've highlighted here with this little arrow. All right, let's do another one. One more, a little bit more challenging. So what's the spherical degree of this mode? Who thinks it's an L equals 0? 1, 2, 3. All right, maybe we'll need to repeat that exercise. So it is an L-gauss free mode. The total number of node lines is 3, 1, 2, and 3. And one of them goes through the rotation axis. So this is a L-gauss free mode, and m equals 1. Right? In reality, in nature, we don't really observe these L-gauss free and higher modes very easily, and that's because of cancellation effects when you actually observe the star in a very far distance. For the sun, we observe high spherical degree modes. So the higher the spherical degree, the more of these, okay, I need to get stuck on this clicker. The more of these patches, which are basically the patches that are hot and cool or expand and contract, the more of these you get. So if you have very small patches, so high spherical degree mode, you can't really, they basically cancel out for a star that's unresolved, and you don't see them. So for stars, we usually observe either radial modes, dipole modes, or quadrupole modes. L-gauss free are rarely observed. OK, so let's move on to where we can actually do asteroseismology. And the good news is that, in fact, almost all stars across the HR diagram pulsate in one way or the other. So this is just a classical HR diagram, temperature versus luminosity. And we can roughly separate them into two groups. So the ones on the left-hand side in blue are what we call classical pulsators. These are O, B, and A stars, which pulsate because of opacity changes in the interior of the star, which drive a coherent pulsation over very long time scales. The stars that I will be mostly talking about today are what we call stochastic or Sol-like oscillators. So these are basically all stars, cool stars that have convective envelopes. And we call them Sol-like oscillators because the first star where we knew that this mechanism is actually happening is, in fact, the sun. So how are the oscillations driven in these cool stars? I've already given it away a bit. It's the convective envelope. So for cool stars, energy is transported in the interior for radiation, in the outer layers through convection. And convection is a very turbulent process. And this turbulence is essentially shaking the star and causing pressure waves. So waves of pressure is the restoring force to travel through the interior. So oscillations in cool stars are driven by turbulent surface convection, and that is a stochastic process. So it excites a mode, it damps it out, excites it again, and so on and so forth. All right, so how do we actually observe oscillations? Well, we need to observe, for example, brightness variations. So as a star is pulsating, it's changing its brightness. So if you monitor the brightness as a function of time, you see brightness variations, which are due to the oscillation modes going through the star. This is a time series of the sun, and you can clearly see the brightness variations with a time scale of about 5 minutes. Now, typically, stars oscillate in many modes at the same time, so it's very impractical to do your data analysis in the time domain. So in every asteroseismology talk, you will always see lots and lots of power spectra. So we basically just take the Fourier transform of your time series and plot everything in amplitude or power versus frequency. And if you do that for the sun, you see this beautiful power axis, which is roughly Gaussian shaped. And you see all these individual peaks, each of which is a single oscillation mode that's traveling through the interior of the sun. You can see there's quite some regular structure in this. And if you zoom in, you can even see this a bit clearer. In fact, it's very regular. And this allows us to define some characteristic spacings that we use in asteroseismology. The first one is the spacing, the average spacing between modes of the same spherical degree, so the L equals 0 modes, for example, and consecutive radial order. So these are two radial modes of consecutive radial order. This is n, this would be n plus 1, n plus 2, and so on. And the spacing between those two is what we call the large frequency separation, delta nu, which you can show to be related essentially to the inverse of twice the sound travel time from the surface to the center of the star, or the sound travel time through the stellar diameter. Now, this equation essentially can be derived from first principles. It's very much related to essentially this dispersion relation for a wave that connects the frequency to the speed of the wave and the length of the cavity that it's traveling through. Now, furthermore, if you make some assumptions about the sound speeds, the Cs is the sound speed here, for example, ideal gas, you can easily show that the large frequency separation is essentially a measure of the mean stellar density, which is shown here. So the large frequency separation alone already gives you a measure of the mean stellar density of the star. Now, you can also measure frequency separations of modes of different spherical degree. Remember, at the very beginning, I showed this cross-section. The stars at different modes of different spherical degree travel to different depths. So this small frequency separation between modes of different spherical degree essentially measures the sound speed gradient, because it's a differential measurement. It depends on how deep the mode travels. Now, the sound speed gradient changes as the star ages. The sound speed depends on the mean molecular weight. The mean molecular weight changes as hydrogen is fused into helium. And hence, this small frequency separation, especially for main sequence stars, is essentially a probe of the stellar age. Now, if we zoom out again, we can also define a third observable, which is quite easy to see. In fact, it's the frequency, what we call the frequency of maximum power. It's essentially the frequency at which this Gaussian-shaped envelope reaches its maximum. This is what we call nu max. Nu max can be shown mostly empirically to be related to the surface gravity of the star with a very weak temperature dependence as well. This relation is not physically well understood yet. We have some ideas, but it's mostly empirical. But if you assume for the moment that it holds, you have two equations. You have nu max, which relates to surface gravity. You have delta nu, which relates to density. So you have two observables that relate to mass and radius. If you know the temperature, you can combine the two to calculate the mass and radius of a star to typical precisions of better than 5 and 10%. So this is essentially the power of asteroseismology, getting stellar parameters of single stars just by measuring these two quantities. You can do a lot more by measuring individual frequencies, and to probe the interior structure, as I've shown through the small frequency separations. So this is essentially asteroseismology in a nutshell. This was my 10-minute crash course. There's a lot more that you can do, but for the rest of the talk, what's important is that you can get fundamental stellar parameters and you can probe the stellar interior by measuring, for example, these two quantities. So I now want to move on a little bit to talk about the revolution that the field of asteroseismology has gone through. And this is I think, quite similar to what the microlensing community is going to experience once we get the space-based missions like WFIRST, or as we heard Euclid as well, perhaps. So asteroseismology, about not even 10 years ago, consisted of doing science on a handful of stars. So here's an HR diagram showing all stars where we were able to detect oscillations prior to about 2009. So we've had a few dwarfs and subgiants and a few red giants up here. This was mostly done from ground-based rate of velocity surveys, very hard work, lots of observation time, and very difficult measurements because the amplitudes are quite small. So the breakthrough started with Corot, the French space telescope that was dedicated to finding transiting exoplanets and to asteroseismology. Corot was very successful in detecting oscillations in red giant stars up here. In fact, it showed us for the very first time that red giants oscillate in non-radial modes, which is something we didn't know before. And non-radial modes are crucial to probe different depths inside the star. So that really opened up the fields to apply asteroseismology on red giants. And then Kepler came along and sort of blew the whole field open and delivered thousands of detections of stars all across the HR diagram, from stars that are even cooler than the sun to subgiants, low luminosity RGB stars, and all the way up the red giant branch. There are about 20,000 data points in this plot, so it's several more orders of magnitude increase over what we had before. And it really sort of kicked off a revolution in asteroseismology just because of the precision of space-based photometry. So we've learned a lot from Kepler about oscillations. One of the things that we learned are amplitudes. So how large are amplitudes of oscillations as a function of evolutionary state? This is the same plot I just showed before, but now I'm color-coding the stars by their oscillation amplitude, and you can see blue are large amplitudes, red are small amplitudes, and you can see that for the sun and solar-like stars, amplitudes are quite small, but as you move up, essentially correlated with luminosity, you get higher and higher amplitudes. So red giants, remember the nu max relation scales with surface gravity. So red giants have lower surface gravity, lower nu max, so you have longer periods. Red giants have longer periods and larger amplitudes. That's essentially what happens if you move up the HR diagram. Further down, you have faster oscillations with small amplitudes. You go up the RGB, longer periods and larger amplitudes. So essentially, it gets easier for red giants, but you also need a longer time series to actually resolve oscillation modes. So the red giants have really been one of the most exciting parts of Kepler asteroseismology, and I'll give you one example. We'll have to recap a little bit stellar evolution theory, which I'm sure you remember, which is basically the fact that stars exhaust their hydrogen in their cores, they move to the red giant branch, and as they move up the RGB, they fuse hydrogen in the shell around the core, and then at some point at the tip of the RGB, they ignite helium in the core, so helium burning starts in the cores of these stars, and they drop down really rapidly to a position in the HR diagram which we call the red clump. And here in this area, marked by this green circle, we find stars that are both helium core burning, these are the red clump stars, and that are not helium core burning. Those are the ones that are still moving up, the RGB stars. But we can't tell. In temperature, log G, luminosity space, whatever you want to use, they lie in the same part of the HR diagram. So how do we tell the difference between the two? Well, Asteroseismology has showed us a way to do this. Here are two power spectra, two red giants observed by Kepler. And you can see a few familiar features. I've shown you the sun before. These are red giants, so they have lower frequencies. These are hour time scales. You can see the L equals 0 modes, L equals 1 modes. I'm highlighting the L equals 1 modes here. And you can see one big difference to what we've seen before in the sun, which is that for each radial order, so each of these is a radial order, but for each radial order, you have multiple peaks. You don't just have one oscillation mode, but multiple peaks appearing. This is caused by a phenomenon which we call mixed modes. Essentially, the pressure waves that are excited by the surface convection, as I've explained before, propagate inwards and couple with G modes, gravity waves that live in the radiative interior. Now, there are many more G modes than P modes, so this coupling can actually excite extra modes at slightly different frequencies, depending on the core structure. And if you look at the pattern closely, you can see that in this star, the spacing between these mixed modes is much larger than in this star. In this one, they're much more bunched together. So if you actually make this measurement and you measure the spacing between mixed modes for lots of stars, you get two clear sequences. One sequence of stars that shows a larger spacing between the mixed modes and one that shows a smaller one. And it turns out, if you look at models, that this is exactly the telltale sign of the core structure of the star. These ones below here are non-helium core burning stars, so those are the ones that are moving up, the RGB. And the ones up here are the helium core burning stars. And the reason why we see this is because their core densities are so different, because one is burning helium in the core and the other ones aren't. So this was really the first time where Asteroseismology made good on the promise of we'd be able to peer inside the interiors of stars and actually learn whether they're burning helium in the core or whether they're not burning helium in the core, and allowed us to separate RGB stars and red clump stars just by measuring the spacings between those mixed modes. Okay, so this is one example. There are many, many more examples that I won't have time to talk about. Rotation, magnetic fields in the interiors of red giants. There were lots of exciting results that followed on from this, but this was one that sort of kicked it off. But instead of talking more about core structures of stars, I want to go a little bit about on exoplanets, on the exoplanet synergy. So Asteroseismology and exoplanets has been quite a nice synergy between those two fields. And the reason for that, and we've heard this already earlier in the week, is that you want to understand your star to understand your planet. And that has been realized during the Kepler mission, and it's realized that it's become more and more important. The reason for this is, of course, that transits measure the size of the planet only relative to the size of the star. So the depth of the transit is RP of our star squared. So you need to know our star to get to your RP. And if you're lucky enough, then you actually find a star that is oscillating. So if you zoom in here, this is Kepler 36. You zoom in, you smooth it a little bit. You can actually see the oscillations by eye. You do your power spectrum analysis. You measure your astroseismic observables. You derive your mass and your radius. You combine it with the transit depth, and you get your radius of your planet. It's a very high precision, typically 5% or better. Now this is, of course, very elegant. You can detect the planet and you can characterize the star, all using the same data. So there's only, it's only a few more details that you need, like a temperature, for example. But generally, you can solve the whole system just using photometry. And we've been doing this trick for quite a few systems over the years. So this is an HR diagram from a few years ago now. Actually, there's been updates, and we have about 100 systems now. But these are all the stars, Kepler exoplanet host stars, and in red, highlighting the ones where we've been able to do asteroseismology and really precisely characterize the host star and hence also the radii of the planets. There's one system in particular that I want to talk about a little bit more detail because it also illustrates that we can learn more about planets from asteroseismology, not just about their radii, but also about their architectures. And that is Kepler 56, which lies right up here. So Kepler 56 is actually a red giant star, and it shows transits of it has two transiting planets, and it is, of course, also oscillating. So here's the power spectrum of Kepler 56. I'm again highlighting the dipole modes, same way as before, and we can see our mixed modes. We can see multiple peaks per radial order. That's the same effect that I've explained before. But if you look very closely, you can actually see that each of those mixed modes is again split into multiple frequencies. So this is a zoom in here in the bottom panel of each of these mixed modes up here, and you can see that all of them are split into triplets, and the spacing between them is roughly equal in frequency. So what's going on here? Well, this goes back to what we discussed at the very beginning, the M modes. The rotational, basically what's happening here is that we observe rotationally split frequencies. So imagine you have a dipole mode. So we have again our red and our blue parts, and the node line this time going through the equator. So this is an L equals 1, M equals 0 mode. And for the M, you can have a -1 or a +1 mode, depending on whether you have a retrograde or a prograde wave. And both of these have the node line going through the rotation axis of the star. Now, if the star is rotating and the orientation of the star is as shown here, so the rotation axis perpendicular to a line of sight, we won't see anything for the M equals 0 mode. And that's because the red and the blue parts just cancel out. But if you start this animation, the star will tilt towards us. And depending on the orientation of the spin axis inclination, we can see that the relative amplitudes of these rotationally split modes changes. At about 45 degrees, we see a triplet. We see all three components. And then as the star points towards us, we will only see the M equals 0 mode, and the -1 and +1 will not show up. So essentially what this means is that the relative amplitudes of these rotationally split multiplets can be used to measure the rotation, the inclination axis of the star. So for Kepler-56, we went back. We see triplets, which means that the star is inclined by 45 degrees, right? So that's a pretty cool measurement, and you might think, okay, you know, what's the big deal? We've measured the spin axis inclination of a star to be 45 degrees. Presumably all stars are randomly oriented in space, so why is this one particularly exciting or noteworthy? Well, it is because we know that it has two transiting planets, right? So by the fact that it has transiting planets, we have automatically measured a very strong spin-orbit misalignment in this system. And this is quite unusual. We've seen spin-orbit misalignments in other systems, but for multi-planet systems, at least, it hasn't really been observed before. So this was strange, and we explained it essentially in a nutshell through a third companion. So here's a graphical sketch of how we think Kepler-56 got misaligned. Here's the red giant. We're looking at it from the right. Here's the line of sight. We have two transiting planets. We know that from Kepler. And we know the spin axis inclination is about 45 degrees inclined, which we also know from Kepler. And then we think that there's a third companion in the system. By the time we wrote that paper, we had tentative evidence that that was true. But let's assume that there's a third companion. And let's also assume that it's inclined to the orbit of the inner planets. What then happens is essentially that the torque of that third companion causes the angular momentum vector of the inner two planets to precess around the total angular momentum vector. So it's essentially the torque precessing the plane of the inner planets backwards and forwards. The same happens for the spin axis of the whole star, and hence you get periodically a spin-orbit misalignment between the spin axis of the star and the inner planets. Now, back then, that was only a hypothesis. Luckily, this planet has actually now been confirmed, thanks to work by a student of Ben using Keck high-res observations. And we now know that this third companion is in fact a planet. We still don't actually know whether it's inclined to the orbital plane, but that's how we think at least this system formed. So this is an example of how we can use asteroseismology not only to characterize the planets, but also characterize planetary architectures by measuring these these spin axis inclinations. Okay, so that's all the science we can do with asteroseismology, a lot of the science that we have done with Kepler. So we've studied the interior structures of stars, we've studied planetary architectures and planetary systems. So what can we do with WFIRST? Now, WFIRST, of course, will have the microlensing survey, and the microlensing survey will give us light curves that we can use to study stars and do asteroseismology. So to actually test this was based on an idea, in fact, from Andy Gould, and myself and Matthew Penny wrote a paper about this. We decided to simulate what WFIRST would see. And to do this, we took Kepler light curves. So here's a Kepler light curve spanning about 1,000 days. And if you zoom in, you can actually clearly see the oscillations. And this is one of the reasons why we used Kepler light curves. They're essentially noise-free for everything that we're interested in here. So we use the Kepler light curves. Of course, we need to do a few modifications. The first one is that we need to degrade the duty cycle. Now, the duty cycle, we've assumed that we have 72 days, twice a year. We've assumed that that's equally spaced in time. If that changes a little bit, it's not really a big deal. It changes the window function a little bit, but generally it's not that important. Then we also needed to decrease the amplitude. So amplitudes of oscillations decrease as you go to the red by about 50%. So that's quite a big hit. So you have small amplitudes in the infrared. That's needed to be taken into account. And then, of course, we added the photometric noise that we expect for saturated stars for WFIRST photometry. So this was a model worked out by Andy, which is probably a bit on the optimistic side since we didn't quite take into account which unknown systematic errors. But this was basically the baseline for this study. So having this simulated WFIRST time series of a red giant, we could now see what the power spectrum shows. So here's the Kepler data power spectrum of the star, and we see beautiful oscillation power axis here. And if you take an autocorrelation of this power axis, you see a beautiful peak at what corresponds to the large frequency separation, right? You expect to have a repeating pattern corresponding to the large frequency separation. Now, how does WFIRST look at this star? So here's the WFIRST equivalent. So this is the same star, but degraded to what we expect the WFIRST microlensing campaign light curves to look like. And we can clearly see that we still detect the oscillations, the power axis quite clearly. It's a bit more noisy, and that is essentially because of the higher photometric noise and the window function. But we can also still very clearly detect the large frequency separation. So this was very promising, and when we did this, we then thought, okay, let's expand it to a few more stars. So that's what we did. Here's simulated red giants in different evolutionary states. On the left-hand side is Kepler. So this is now in log-log space. So essentially what you're looking for is a power axis hump, which are the oscillations here and here. So these are three Kepler stars, a high luminosity red giant, a clump giant, and a low luminosity RGB star. And these are the simulated WFIRST light curves. And you can clearly see the high luminosity red giant, not a problem. The clump star, also not a problem. For the low luminosity RGB stars, it gets, basically we don't see the oscillations anymore because the photometric noise is too high, assuming that the star is in the bulge. However, this is still very, very promising because there are a lot of clump stars out there. And in fact, if you do the calculation and you say, okay, let's simulate a population in a typical microlensing field, and count up the numbers of stars in a cumulative way as a function of apparent magnitude, and then say, okay, for a typical bulge giant, we can detect oscillations down to about the red clump, and you draw a red line to the absolute magnitude that corresponds to, and you find the intersection of that, you see that we expect about 1 million detections in a microlensing field of oscillating red giants. Remember, for Kepler, I said it was about 20,000. With WFIRST, we're going to increase that by a couple of orders of magnitude. So now you might ask yourself, okay, well, we've got 1 million more red giants with oscillations. Who cares? We've got 20,000 already. What is it that we can learn about stars or anything else with these new detections? And the answer to that is galactic archaeology. We've already heard about this yesterday in a couple of very nice talks. Galactic archaeology is essentially a very exciting and rapidly developing field in studying stellar populations in our galaxy, trying to answer questions like how old is the galactic bulge and the halo, the thin disk and the thick disk, how important is radial migration, so where stars are born, do they migrate outwards or inwards, and how does that affect our understanding of the Milky Way. Now, galactic archaeology and the synergy between astroseismology and galactic archaeology has been realized before. In fact, the K2 mission has a dedicated galactic archaeology program that is looking at different parts of the galaxy. So all of these are different K2 fields along the ecliptic plane. And these are simulated red giants where we believe we'll be able to do astroseismology on. So you can see that K2 is fantastic for this sort of stuff. It's looking at different directions in the ecliptic plane, and it's basically probing different populations of stars and red giants all across our galaxy. So K2 will make a lot of progress in this field. To show it a little bit differently, here's the galactic plane, and here are the K2 fields across the ecliptic plane. And of course, there are fields that are in the plane towards the bulge, and Kellen talked about this earlier in the week, which is the microlensing campaign from K2. But for asteroseismology, there are a couple of very big obstacles here. First of all, we have crowded field photometry, so the pixels are large. We don't really know which star the oscillations are coming from. But also, the time series for K2 are quite short, 70 days, and that limits you as to how evolved the star can be in order for you to do asteroseismology. Remember, stars that are larger, more evolved stars have oscillation periods that are longer. So you need long time series to resolve those modes, measure the large frequency separation, and do all the science that I talked about. So this will limit K2. It will still be very successful in probing populations sort of nearby. So, well, not really nearby, but quite. So this is basically a histogram of the distances of red giants, astroseismic red giants, that we can expect with Kepler and K2. And Kepler is the green histogram, and in red is K2. These are not actually astroseismic distances. It's basically an extrapolation based on different stellar classifications, but it won't be too much different. So you can see that the K2 galactic archaeology program is essentially probing out to a few kiloparsec, and that's going to tell us a lot about the thin disk and the thick disk, but not really outwards down here, especially towards the bulge. We won't have too many detections. But if we go back to WFIRST and say, okay, how many stars do we expect to detect oscillations with WFIRST, and how far away are they, we get a result that looks a little bit like this. And you can see that WFIRST will really open up this field in terms of two things. First of all, the numbers. I've already talked about this. A couple of orders of magnitude increase in the number of detections. But also the reach, just being able to probe much further by the fact that we have longer time series, can detect oscillations in high luminosity red giants that are quite faint and in the bulge mostly. So this is very exciting. It basically means that for galactic archaeology, we will be able to measure ages in the galactic bulge, and perhaps measure, actually with red giant populations, the age of the bulge in the galaxy. Okay, in my last couple of minutes, I want to talk a little bit about what WFIRST asteroseismology can do for exoplanets. So similar to the Kepler-56 analogy that I've given before. So to do this, I've looked at a synthetic population of a WFIRST field, so similar to what I've shown before. And if you highlight the number of stars, or the stars where we expect to be able to do asteroseismology on, this is a familiar result, mostly the red giants that live up here, and a few low luminosity RGB stars. Now, for transiting exoplanets, Ben, immediately after me, will tell us all about the exciting results that we can expect for stars down here, the more unevolved stars. Unfortunately, the limit probably for detecting about a Jupiter radius transit will lie more or less exactly here where the astroseismic detections stop. So it's unlikely that we will have this nice synergy between transiting exoplanets and asteroseismology with WFIRST. However, there is a lot of stellar astrophysics that you can do down in the regime where we will be able to find transiting exoplanets. And I just wanted to flash out a few. You know, asteroseismology is very nice to do stellar astrophysics, but there are many, many other physical effects that you can study with time series photometry. You can study rotation periods of stars. You can use gyrochronology to derive stellar ages. You can study flares in M dwarfs. This has been done. All of this has been done with Kepler, but I don't see a reason why it shouldn't be done with WFIRST. Flares in M dwarfs. You can study granulation. So this is also known as flicker. It's basically brightness variations to the granulation on the star that have been shown to be quite sensitive to surface gravities, mostly for these subgiant and more evolved stars here. So I think there's really a lot of stellar astrophysics that the WFIRST microlensing campaign will enable, and that the community perhaps hasn't quite realized yet, but I'm sure we'll get quite excited about once we get closer to the data. All right, so my last minute I'm going to spend, which is perhaps telling in a way, on asteroseismology and microlensing. Now the overlap between those two is of course a bit limited. We know, and we've heard many times this week, the typical lens star is an M dwarf. There's nothing you can do with asteroseismology and M dwarfs. We would really love to, but the amplitudes are just way too small. But you can have a synergy if you care about the source. Now, we've heard just before that large source stars are actually not good, but some of them will be red giants. So some of the source stars will be red giants. And if they are, and we can do asteroseismology, then asteroseismology can help, because we can basically, by the fact that we can measure the radius, infer the distance, and hence also the angular size of the source. Of course, just having the radius, you still need a temperature, and you still need to deal with extinction. But it's something to keep in mind that asteroseismology can help if you're worried about, if you have a source that you believe is a red giant and you see variability in your light curve, then talk to an astroseismologist. And finally, one thing that I thought about, which I'm not sure will be relevant, but if it is, it's something to keep in mind, is stellar variability. In fact, it was mentioned early in the week that sometimes if you have a giant stars are variable, and if you have a microlensing light curve, that variability might show up. These are light curves of K and M giants observed by Kepler, and you can see this wide range of variability, and sometimes with very large amplitudes, right? This is exactly the effect that I've talked about. Stars pulsate and granulation, all this kind of variability that comes in. So this variability is, of course, signal for us, and it's noise for someone who's interested in microlensing, and vice versa. But the point I wanted to make is that this variability we actually understand, and we can model it in the time domain. This is something that's gotten really important and more important now. This is work done by my graduate student Sam Grunblatt at the IFA. This is a transiting planet orbiting a red giant star. And you can see the transit here, but you can see all this out-of-transit variability. It's all the star. And basically, it's preventing you from measuring the transit depth very accurately. So what we've been trying to do is actually model the variability due to oscillations and granulation in the time domain. And you can do this. We know we have pretty strong priors as to what the time scales of these variabilities are, what their amplitudes are. So you can mitigate the effect if you have signal or variability in your light curve, in your microlensing light curve. You could easily think of an example where this is a microlensing event or an anomaly where you have some variability by the source star. This can be modeled, and it's possible to take into account. Okay, so I'm already over time, so I will leave up my summary and take questions. Thanks very much. So I would disagree a little bit that with spectroscopy we have a good handle on the radius. It depends on what precision you talk about, but there are some sort. Yeah, I agree with that statement. So yeah, I've focused on radii and masses because those are sort of the quantities that we get directly out of a transit light curve, for example. You want to get the radius of a planet. But you're right, ages you can get from astroseismology much better than you can from isochron fitting. So there are, astroseismic ages are not model independent. So that's something that's important to keep in mind that sometimes isn't that discussed. But essentially, the frequencies that you get, you need to compare them to a model. And that model has physical ingredients that might change, right? So you can treat your mixing length differently, convective core overshooting, all these sort of ingredients. So if you take all these systematics into account, which has been done, and say, okay, our model frequencies, you can get ages to about 10 to 15% for main sequence stars. If you go to red giants, it gets a little bit more complicated because this trick of the small frequency separation that I mentioned doesn't quite work anymore. So you actually get your age for your mass. If you look at the red giant branch, the age of a star is determined by mostly two factors, its mass and its metallicity. If you have those two, you can get pretty good ages as well, assuming you have a handle on mass loss if it's already past the tip. But generally, the number to keep in mind is 10 to 15% age is a routine from astroseismology now for main sequence stars and subgiants.
That's better than a factor of 5.
Yes. I actually do have a backup slide, more or less. So this is so absolutely yes. Right. So you can get a so essentially yeah, we thought about this. So you can get the radius through the parallax and the bolometric flux essentially, and then you can so that one scaling relation that I showed, the new max scaling relation, the one we don't actually physically understand from first principles, you can just toss it away and say, okay, I have a radius, so use delta nu to get a mass. So you can play the exact same game, except for that, you know, the transit-derived densities are hard, right? You need to know the eccentricity. You don't know that. You know it for transiting exoplanet hosts, but you need to have a handle on the eccentricity because there's a degeneracy between those. Sure. Yeah, there's many ways you can combine the different observables to do this sort of inference. So the bottom line is that Gaia will be very helpful to calibrate astroseismology, which is essentially what we did in this paper. So we published a paper. I didn't have time to show this, but this is the radius derived from the Gaia parallax compared to the radius from astroseismology using these scaling relations that I've shown before. And you can see that it agrees pretty well. There's no metallicity strangeness. So the metallicity is color-coded here. And there's some structure in the residuals. The error bars are quite large with T-gas at the moment, but once Gaia DR2 comes out, we'll do exactly that. Yeah. That would be fantastic if there would be. I would love to have a Rossiter-McLaughlin measurement. Unfortunately, I think the planets are quite small. They're too small. They're basically Neptunes. I think one of them is between Neptune and Jupiter. So it would be a very hard measurement. We haven't actually tried. Maybe Ben can comment, but I think it'd be a hard measurement for Kepler-56. That's right. Yeah. So it's a red giant star. It's not rotating very rapidly, but there is a single system where we have both. It's not a red giant system. It's a main sequence star where we have asteroseismology and the Rossiter-McLaughlin effect. And in fact, you can combine the two because they're not measuring the same thing. So the asteroseismology is measuring the spin axis inclination to your line of sight. Rossiter-McLaughlin is measuring the projected obliquity of the system. And actually, if you have both, you can actually solve for the true obliquity. So you can't actually compare them directly, but you can combine them to actually get the real 3D obliquity angle. But unfortunately, we've only been able to do that for one system so far, but hopefully there'll be more in the future. How do so I mean, so the pulsation is, we're assuming that the pulsation modes are aligned with the rotation, with the spin axis of the star. And that is essentially given, I mean, if you have, I guess you can have misalignments of magnetic field axis and rotation axis, but for pulsation modes, I think from first principles that's not expected to happen, just because of the spherical symmetry, I think. But we don't expect, I mean, there are cases for stars different than solar-like oscillators where you actually do have misalignments of the pulsation axis and the rotation axis and the magnetic field axis, but these are not the sort of stars I talked about. These are sort of AP stars, rapidly oscillating AP stars, but this has been observed. But as far as we know, for these sort of solar-like oscillators, that's not a problem.